Okay, so I'm going to keep doing 10.3. We're in focus. So I'm going to do, but by the way, this is just example 1 in 10.3. It is in the book. This is about a spring mass dash pot system. So we talked about these, it's a while ago now, but so we have this mass. It's attached to a spring, which is attached to the wall, and we know that the spring obeys Hooke's law. So the spring, the force applied by the spring is negative kx, where x is like the displacement between the mass and the natural position that the spring wants to be at. Meanwhile, there is a dash pot, which is this device that just opposes any velocity. And the dash pot has a certain strength, like this coefficient c, that kind of tells you how much it opposes how much velocity. And so the force that it applies is c times x prime, where again x is the displacement. So if the mass is moving, then this pushes it. This applies a force in the opposite direction of movement. So the total force acting on this mass would be, of course, m times the second derivative, first of all, but it would also be the sum of these two forces. But anyway, we derived this before. I was just reminding you. So for us, that's 1/2 x double prime equals negative 17x minus 3x prime. And then let me get everything over here and multiply it by 2. So I'm going to get x double prime plus 30. Whoops, let me put this in order as well. 6x prime plus 34x equals 0. There we go. So this is a second order, linear, homogeneous differential equation with constant coefficients. This is, and maybe you're sick of me saying this, but this is something that we could solve in another way. We would write r squared plus 6r plus 34 equals 0. We solve for r. We do all that stuff we know how to do. But, as you probably guessed, I'm going to say we're going to do it with Laplace transforms. So I'm going to do the Laplace transform of both sides. How do we do the Laplace transform of x double prime? If you remember, it's s squared x minus, and then it's a smaller power of s, so now I went from s squared to s, and then I start multiplying by the initial conditions. So I'm going to start with x prime. Wait a second. No, I do s times x naught, don't I? Well, it's a good opportunity to check. Obviously, my memory's not so good on this. Yeah, okay, I was right the second time. Yeah, you go down a power of s, and then you start with no derivatives. The next term would have f prime, and the term after that would have f double prime. Okay. All right, there we go. So I do s times this, so 3s, and then now I'm going to subtract. Now I'm down to s to the 0, so this is going to be my last term, and I multiply it by this. And s to the 0 is just 1 anyway. So that's the Laplace transform of x double prime. Then I'm going to have plus 6 times the Laplace transform of x prime, which is s times x minus, and then really this is following the same pattern. It's just going to be shorter because it was just x prime instead of x double prime. I would subtract. The next power of s down is s to the 0, so there's not going to be any s's. and I start here, so 3. Yeah. Plus 34 Laplace transform of x, and then Laplace transform of 0 is 0. Okay, so there we are. Let me collect all the x terms. S squared plus 6x plus, oops, I was factoring out x, so I didn't need any x's in there. Let me go ahead and get everything else to the other side. So I would have a 3s, I would have a 1, I would also have an 18 from this. So let me write 3s plus 19. Actually, sorry, let me make sure that I'm actually, yeah, that's what I'm supposed to get. Okay. So x is 3s plus 19 over, ooh, yeah. Where I put an x here, that should have been an s, yeah. Because that was from this 6sx. There we go. Right, anyway. That's what goes here. Okay, and now I just need the inverse Laplace transform of this to find my original little x. So this is, again, it's a partial fractions problem. We should try to factor the bottom. We can do this the easy way, thinking of two numbers that multiply out to 34, but all I can think of is, well, there's 1 and 34, and those don't add up to 6. There's 2 and 17, those don't add up to 6. So I'm out of ideas. I can also do the quadratic formula. Like that. Oh boy, what is this? This would be 136. Oh, that's nice. So 36 minus 136 is minus 100. So this is negative 3 plus or minus. This would be 10i, so then I divide it by 2, 5i. Okay. Oh. Yeah, maybe I don't care too much about what this is. The point is that it's a complex number, so actually this does not factor. For our purposes here, we don't consider complex numbers to be like a factorization. So we are going to do something else. We're going to complete the square. Remember how this goes. I take the denominator. I'm going to say this is s plus 3 squared, because 3 is just half of 6. And then I need to fix this somehow, because this would be s squared plus 6x plus 9. What I actually want is 34, so what's missing is 25. So x is 3s, 3s plus 19 over s plus 3 squared plus 25. And remember how I want to do this. Now that I know I have an s plus 3 down here, I would like all my s's to appear as... I want all my appearances of it. Okay, let me start over. I want my appearances of s to all be in parentheses with a plus 3. And this one isn't like that. I could make it like that. But I need to fix something. This would be 3s plus 9. I wanted 3s plus 19, so what's missing? There's a missing 10. So, but now I'm good. Okay. Now, just to be clear about what's happening, I'm breaking this up. I'm breaking up the numerator. And by the way, this is something that I'm allowed to do. You can break up the numerator of a fraction. You cannot break up the denominator. So little x is the inverse Laplace transform of this. Okay, so now let's talk about how that goes. First of all, we need to remember the rule for translation, which is this one, the inverse Laplace transform. If I have s minus a instead of s, then I get this. And I have to combine that with some of the rules that I know from 10.1. So let's start to think. If all the s plus 3's were s's instead, where would I look on the chart? I would probably look here, because what I would have is 3s over s squared plus 25. Whoops, not here, I meant here. So, right, how should I do this? If this was just an s over s squared plus 5 squared, because I've got 25 here, this would be cosine 5t. There's a 3 there, so I should multiply by 3. Also, it's translated. This translation, if you remember, this is like a would be negative 3 because I have s plus 3's instead of s's everywhere. So what happens is you just multiply the inverse Laplace transform by e to the at. So I'm going to multiply this by e to the negative 3t. That's the effect of what happens because these are s plus 3's instead of s's. Okay, let's do the next one, because I still have to find the inverse Laplace transform of this. So I would look at my chart. This one does not have any s's on the top, so this is going to be more like this. K would be 5, and I'm supposed to have a 5 on top then. Actually, what I have is a 10 on top, but that's okay. So this 10 has an extra 2 factor, so I'm going to put 2 here, and then sine of 5t, because that's the formula I was looking at. And because these were s plus 3's instead of s's, I do e to the negative 3t. Yeah. And let me just make a comment that this answer makes a lot of sense. I started talking about how we would have done this the old way. This is like the characteristic equation way, where you write r squared plus 6r plus 34 equals 0, and you solve for r. Of course, as I've pointed out, the characteristic polynomial came out anyway, because this is actually the same polynomial, s squared plus 6x plus 34, and just instead of r squared plus 6r plus 34. And we did factor this. The factors that we got were the roots that we got were -3 plus or minus 5i. And so then we should have expected an answer, because if these are the roots of the characteristic polynomial, of course our answer is going to involve, oops, sorry, I'm just trying to scoot the paper up. If this is -3 plus or minus 5i, you do e to the real part, so e to the -3, and then you have a cosine of the complex, like the coefficient of I, and then you should also have a sine counterpart to the cosine part. So we really should have expected an answer, at least of this form. That argument that I just described doesn't explain this 3 and this 2. To get this 3 and this 2, you would have to go back and use the initial conditions. For us, that part just worked differently. We use our initial conditions almost at the very beginning. When we take the Laplace transform of both sides, we're already having to plug in information related to the initial conditions, and from then on out, we don't really have to worry about it again because that information has already been plugged in. Anyway, let me upload this.